Welcome, welcome everybody. I am very excited, a pleasure to introduce the speaker today for our MICDE webinar, Dr. Udo van Toussaint. Dr. van Toussaint is from the Max Planck Institute for Plasma Physics in Garching, Germany. And he is also the group leader for the Plasma Material Modeling and Foundations Group. Dr. van Toussaint earned his PhD in physics at the University of Bayreuth, Germany in 2000, and then worked as a postdoctoral researcher at NASA Ames in Mountain View, California for 2 years. And since 2003, Dr. van Toussaint has been a scientist at the Max Planck Institute for Plasma Physics. And Dr. van Toussaint is also the editor of the journal Entropy. So one major area of interest for Dr. van Toussaint is in plasma physics and plasma wall interaction. But additionally, his research also focuses a lot on methods of statistical analysis, uncertainty quantification, and machine learning. For example, in Bayesian experimental design of computer and physics-based experiments, uncertainty quantification of complex computer codes, such as those that you find to describe plasma physics phenomena, and active learning systems that can dynamically and adaptively decide what actions to do next, that can give you the most information based on the results that you have observed in the past. So a lot of Dr. van Toussaint's work encompasses the developing and advancing machine learning and statistical techniques, such as in hidden Markov models, neural networks, Bayesian acyclic graphs, Markov chain Monte Carlo, sequential optimization, polynomial chaos expansion, and many, many more. So Dr. van Toussaint, welcome. And thank you very much for giving a presentation today. And we look forward to hearing about what you have to say. So please take it away. Thank you very much.
So thanks for the nice introduction. Good morning, everybody. It's a pleasure to have the opportunity to present some, let's say, results, how to combine the Bayesian approach with artificial neural networks. So typically, there appears to be kind of a contradiction between the two approaches. In a Bayesian approach, you specify prior knowledge as good as possible, and then essentially Bayes' theorem tells you how to proceed. So in many cases, this is a highly defined system. Artificial neural networks, however, are often used when there's only vague information available, and they are commonly labeled as black boxes, which perform surprisingly well, but why is often unknown. And traditionally, there was kind of attitude, okay, Bayes with the prior terms needed and artificial neural networks don't go well together because it's simply impossible to come up with a reasonable prior for the weights and other parameters which enter there. I hope I can show you today that this is not necessarily true. And if you improve upon the standard approach, that you can really gain in performance and also in insight. So let's switch the slide. That was the plan. Okay. The talk is essentially first motivating why a Bayesian approach is highly beneficial, then a very brief introduction to neural networks, and then how we can combine these two approaches, how we can come up with a suitable prior for the weights, and once we have that, what can we do with this combination? And then, yeah, finally, conclusion. So why Bayes? If we look how we learn in science, what is the scientific inference cycle, then we see that we typically have 4 steps. So at some stage, we have some experiments which yield results. These results are then, in the second step, evaluated and are used to form subsequently some hypotheses which aim to summarize the experimental results so that we learn something from these experiments. And once we have some hypothesis, then the next step is how we can falsify these hypotheses, which experiments are needed to, let's say, exclude other hypotheses so that the remaining hypotheses have a lot of experimental support on that. And since these individual steps appear over and over again, they are commonly assigned names. So the first level of statistical inference is often parameter estimation based on the experimental results. And once we have probability distributions on these parameters, then we proceed forwards to perform model selection. So which models are adequate given the quality and number of the data, and depending also on the complexity of the model. And then how can we best come up with experiments which falsify these models, so labeled experimental design. And then we repeat that cycle. However, to be able to do that in a consistent manner, we need a tool which provides us with means for consistent reasoning so that we can have a quantitative measure on which we base our evaluation criteria. And if we look at that, then the key step in science is that we have some prior information, that may be prior experiments, that may be earlier hypotheses, which we want to combine with new data to get additional insights so that we acquire new knowledge. In logic, there are essentially two different approaches of consistent reasoning. The one is deductive reasoning. So given that we know the cause, then what is the associated outcome? What are the effects? So the classical example for that would be, we know the properties of a coin. So for example, that it is a fair coin, and then we can compute what is the probability of having to observe 7 heads, given that we have 10 tosses. So that's straightforward, but that's not the way of reasoning which we have in science. There we have to apply inductive reasoning. We have some observations, some effects, and we know want to deduce what are the possible causes. So we have to perform inductive reasoning. If we stick to our previous example, then it would be something like, we have observed 7 times head out of 10 tosses. What is the probability of this coin to be fair, or approximately to be fair? And for this kind of inductive reasoning, we need the corresponding tools. This problem has been posed already very early, and already in 1946, Cox derived that with very basic elementary requirements like transitivity, consistency, the usual rules of probabilities are the ones which are adequate to handle uncertainties. And the debate which was later on going on was more what means this kind of probabilistic description. And here we have two different schools, essentially. The Bayesian interpretation, where the probability of X given some prior knowledge, I describe how probable or plausible X is distributed for the possible choices at hand. So essentially, it is given that we have limited knowledge, as we essentially have always, what can we tell about the distribution of X given that limited knowledge? The frequentist interpretation is different from that. Here we have to use infinite ensembles, and then the probability describes how within that infinite ensemble the X is distributed. So this is conceptually quite different, but is often mixed up. However, given that we have decided to follow Cox, then essentially the rules, if we stick with the Bayesian probability of managing the different probability distributions, are very familiar. They are the classical ones. In a Bayesian framework, you always have conditional probabilities because there's always some prior information available. And that means all we need is to have a means to manipulate conditional probabilities. And the only ones which essentially are available and consistent with the axioms are the familiar sum rule, how to combine different probabilities, and the product rule. And this is essentially the mathematical framework where Bayesian probability theory rests on. And from the product rule, immediately Bayes' theorem follows, which is the central cornerstone of this approach. If we have a closer look at the product rule, the probability for having H1 and D can be written either as the probability for observing D given H1 and the prior knowledge times the probability of H1 given I. But since the order in the first argument is irrelevant, we can expand the same quantity also differently as the probability of H1 given D and I times the probability of D given I. And if we now equate those two lines on the right-hand side, then we get Bayes' theorem, which tells us the probability of H1 given D and I can be written as these terms in the nominator divided by the denominator. So that's a very elementary consequence. Why is it such a central piece in the Bayesian framework? These individual terms have all names. So the one on the right-hand side of the denominator, P of H1 given I, we will later equate H1 as the model or the hypothesis, is called prior. Then the probability for D, which we will later assign the meaning data, given the model or hypothesis H1 and I, is called the familiar likelihood. And the product of these two is proportional to the posterior distribution, which is the probability of H1, the hypothesis or the model, given the data and prior knowledge. And there's a normalization in the denominator, which takes care that everything is nicely normalized. As you can see, if we compute the posterior, then it's not only given by the likelihood, but also multiplied by the prior, which of course immediately implies that a maximum likelihood approach is not the same as the maximum probability for a model given the data. And this is very important to keep in mind, because what we are interested in physics or engineering is what is the most likely model parameter given the observed data. We are typically not interested in the likelihood, which describes how likely the data is given a model. An example which shall illustrate that: the probability that a street is wet given that it rains is quite different from the probability that it rains given that the street is wet. There could be other reasons, like somebody was washing the car or similar like that. So confusing posterior, which is the quantity which we are interested in, and the likelihood is causing often quite some problems. So we are interested in the posterior. This is the one which is of interest, given that we have observed some data. A consequence of that is, if we stick to that, is that we can not only estimate parameters, the most elementary step, but that we can also proceed from there to model comparison. So given that we have different competing models which explain the data, maybe with varying degrees of quality, then what is the more likely model? And it's obvious that we cannot simply rely on the best fit, because typically the more complex models are always providing a better fit, and then we would end up with models which describing the data very well but are highly unstable. Within the Bayesian framework, a quantity Occam's razor is automatically included, and this is highly beneficial. Where does it come from? This is a consequence of the normalization constant, which I was skipping over in the previous slide. I should mention a crucial point. Unlike in the classical statistic, where one has something like a null hypothesis, so one can provide a number if something unknown is happening, this does not happen in a Bayesian framework. In a Bayesian framework, you can only compute model probabilities if you explicitly specify these models, because there could be that there is no alternative explanation, and then even an unlikely model may be or has to be true. So in Bayesian framework, you always have a complete set of models. So given that we have a complete set of model, then we can compute the probability how likely a model is, given that we have observed some data. Let me guide you through that. So the probability for a model, let's say MI, given the data, is again given by Bayes' theorem. That's the prior probability for the model. If we have no reason to prefer one or the other, this term could be set equal or constant to all of that. Then the likelihood for the data given the model divided by some normalization. The problem is, how can we evaluate the likelihood for the data given a model? And this is where a typical Bayesian trick comes in. If we would have a parameter for the model, or a set of parameters, we could compute the likelihood for the data given the model, but in the initial expression, these parameters are missing. Here we can now apply the marginalization rule, which means we can introduce these parameters like it's shown here under the integral, and then average over all the parameters weighted by the respective probability. And this is now a quantity which we can compute. And with that, we can then compute the probability for a model. And this allows to rank models, and later on also neural networks of different levels of complexity, because there we know the parameters, which are the weights, and then all we have to do to compare these different network models is to compute this integral. Where does now the effect come from that overly complex models are penalized? Essentially, it is a consequence of this integration. Here we have again the probability for the data given some model, which we can compute by the integration of all the model parameters, the likelihood of the data given these parameters times the prior probability for these parameters. And if we now sketch how these different contributions look like, then typically the likelihood is different from zero only in a very narrow range of the parameters, but the prior probability distribution has to be normalized. So if we have a lot of parameters, then each individual prior configuration has a very low probability. And since the probability for the data given the model is the product of the two, the more we have unused prior volume, where the model doesn't have a high quality of fit, the lower is effectively than the resulting model probability. So models with more parameters eventually yield a very narrow peak with a very high likelihood, but the volume where this happens in the total prior and parameter space is very limited. So essentially those overly complex models are penalized for the wasted volume. So parameters which are not parameters combinations which do not contribute to the regions where we have a high likelihood. So after this very short introduction into the Bayesian framework, where I essentially wanted to motivate why we need a prior on the parameters, because only then we can exploit the full power of the Bayesian approach, let's switch to networks. So essentially what we see right now is the third wave of artificial neural networks. The very first one in the late 60s, 70s, with essentially linear activation functions was killed by the insight that these networks were nothing more than linear mappings. So matrix algebra can simply replace them. Then there was a second wave in the early 90s, maybe up to the late 90s, where they succeeded in having quite some respectable results, but were later essentially overcome by other tools like support vector machines. And now, I would say, starting 2006, 7, there were increasing record-breaking successes of neural network approaches, and this essentially triggered the present wave where neural networks are now used for a large number of applications, far extending from the original playground of image classification and segmentation to the application of neural networks for physics-inspired PDE approaches. And I think it's pretty safe to say that this third wave will persist for quite a while and is here to stay. It's also funny to notice that previous insights, which were well known in the late 90s, I can highly recommend the book by Bishop, keep getting rediscovered. And yes, so that also indicates that the memory of science is limited. Okay, how does the standard neural network, feed-forward neural network look like? Essentially, we have some input layer with a maybe large number of different inputs, some bias. Then these inputs are superimposed by linear combination with some weight parameters, and then some nonlinear weight function is applied, activation function, typically ReLU or tangents hyperbolicus. Important is that there's some nonlinearity in there. And then propagating through several hidden layers, one summarizes the result of the network in some output layer, and then the performance of the network is optimized by optimizing the individual parameters. And these networks have typically nowadays tens of thousands of parameters and multiple layers, but the underlying mathematical description is more or less identical. The overarching question is, of course, which network structure? So how many layers? How big are these layers? Shall the neurons be connected all to all, or maybe just neighboring neurons? A convolutional approach, something else? Essentially, at present, this is mostly a kind of black art. There is some experience which approaches work, which ones less. And of course, there's always the problem, if you make your network more complex, then it is better on the training data, but performs worse on the test data. And in general, you don't have a lot of insight about the optimal bias or trade-off between bias and variance. So it is commonly acknowledged that to have a good and robust network, you need some kind of regularization that can be either achieved by algorithmic means, saying that you use approaches like early stopping or dropouts, or that you, in your measure of quality, you add some regularization, like some penalty term, which penalizes, for example, weights on the connections which are too large. And then, of course, the question is, which regularization? And over the years, there have been a lot of proposals being made, for example, that you have as regularization term the sum of the squares of the individual weights. Then it was noticed that this is not very beneficial, although that's something which you still see very often recommended. But the thing is that for this simple weight decay, the network favors a lot of small weights instead of focusing on the more relevant weights. So there have been proposals like modified weight decay, which essentially introduces some kind of threshold, gamma. There have been proposals like curvature-based regularizations, which operate in the output. But these are all pretty much ad hoc. From a Bayesian point of view, all these regularizers are essentially imposing some kind of prior probability distribution over these network parameters. And then, of course, you can apply Bayesian theory. But the key point, which is still unaddressed, is which prior probability distribution? And like in linear regression and other things, people say, oh, maybe a flat prior probability distribution should do, which is obviously not a good choice, but essentially it is unresolved which one to choose. But if one has a closer look into that, this is not quite true. If we look into the properties of the typical activation functions which are used for networks, then we see that essentially what is happening, they combine the k-dimensional input weighted by the weights on each input coming into the neuron, and then apply some nonlinear activation function, which essentially acts like a decision boundary in this high dimensional space. So if the input is smaller than some value, you get either 0 or a small value. If it's above a given value, you get a larger response or approach 1. So essentially, this input, which is composed of the weights times the input vector and some bias, is essentially putting a k-1 dimensional hyperplane into this k-dimensional space, separating more or less left and right. And then a reasonable prior for that is, given that we don't know anything about the inputs, how shall the distribution of these separating boundaries be in the weight space? And since we don't know anything, of course, no orientation shall be preferred, which means that the position of these decision boundaries have to be invariant under translation and also under all possible rotations in that hyperspace. And if we have, by some means, been able to come up with that, let's say, formalism, how to make these planes uniformly distributed in the weight space, then we have a suitable prior for the neuron weights. And I will guide you on the next few slides how one can actually do that computation. So what we want to have is a prior distribution for the weights A, which are related in a very simple manner to the standard neural network weights W. And the orientation and position of this hyperplane in the input space is given by this linear equation. Since we want to have this probability distribution of the parameters independent under some transformations, we have to express that in a functional equation where the probability of A in some volume element over the input space has to be identical to the probability distribution volume element A prime in the transformed coordinate space. This requirement essentially yields to a functional equation for this probability distribution for the vector A, and following, for example, the derivation in Kendall, one can transform this very challenging functional equation for a class of transformations, infinitesimal transformations, into a differential equation system, which is easier to solve. And for simple transformations, here on the right-hand side is an example. The transformation is often very simple. So this differential equation then can be solved. And once this is solved, one has the probability distribution. So let's make a very simple example. Let's assume we have a vertical line, which is given by A prime x prime plus 1 is equal 0. And we want to have the position of this vertical line uniform. And then the question is, which prior do we have to impose onto the probability distribution for A prime? Since we have only translation is the 1 degree of freedom, we can write once the equation for that line as A1 x1 plus 1 equals 0. We can then transform our coordinate system by a translation shift by epsilon. We express that equation in the prime coordinates and then solve for the relation between A and A prime, which is the same as on the slide before. We need some relation between the two different coordinate systems, which is given here, that x1 times A1 prime divided 1 over plus epsilon, that's the infinitesimal transformation. A1 prime plus 1 has to be equal 0. And if we now expand that to the leading order in epsilon, which is sufficient because we are considering infinitesimal transformations, then we get our transformation equation. T of epsilon of A is given by A plus epsilon A squared. Then we plug that into our transformation invariance equation, which, if we just solve for these individual terms, yields an Euler equation, differential equation, and then we get as a result that if we want to have a uniform density of these vertical lines in the parametrization A times x plus 1, then the only probability distribution which does that is 1 over A squared. On first glance, that looks a little bit strange, but if you just consider what would happen if in this translation you would plug in different values of A, then you would see, if you use a uniform probability for A, that you get accumulation of lines near 0, because essentially large numbers would all be mapped towards small values, whereas if the probability for large values of A is decaying like 1 over A squared, you get essentially a uniform distribution. So this approach does work. And now we can go back to the problem how we do that for a neural network. Essentially, it's following precisely the same lines, except that we have now, instead of a one-dimensional case, we have an k-dimensional space. And if we do the same mathematical transformation, then we end up with this probability distribution, which is essentially a multivariate Cauchy distribution. And if we say, okay, we have only one input, then we end up with a well-known case for a straight line prior, that to have uniform distributed prior for the slope of a straight line, that it has to follow this distribution. So far I was talking about the weights, but we have also a bias term for the neural networks, and there one can apply the principle of maximum entropy. So which probability distribution for B yields the most uninformative probability distribution, and then using standard maximum entropy approaches, this can be evaluated as well. Combining now everything, we have now a probability distribution for neurons, for the parameters weight and bias, which is given here in that yellow box, which looks a little bit scary, because one has to sum over all weights which are coming into a cell, then over the different biases if we have more than one neuron in a layer, and then essentially have to do that for all layers. So this is the probability distribution, the prior probability distribution for the network parameters A and B. Okay, how does it perform? One can study the individual properties of that, and essentially it turns out that this specific probability distribution has several very nice properties. So first of all, if a neuron is not needed in describing the result, this prior drives it to zero, so it erases individual cells which are not necessary. So a kind of intrinsic dropping of cells. The same, interestingly, holds also for complete layers. So if a layer is not doing something beneficial, it is essentially just mapped to the identity transformation. So that blends very well with ResNets, which are a very nice and recent extension. And of course, having that, it's possible to address which of the inputs to the different neurons are the most important ones. So far I was essentially talking, okay, let's do some mathematics, and is it possible to derive a prior? And under the assumption that the decision planes have to be uniform in weight space, it's possible. So now we have all the ingredients in place to apply that, the full Bayesian machinery, because now we have a prior, we have the likelihood, which is given by the model, and now we can also use the Bayesian machinery to determine which networks are the most appropriate ones given the data. So we don't need a lot of data in that case, because if we have very few data, then the Bayesian machinery will tell us, okay, you cannot make good predictions, so very simple networks are sufficient. If you have a lot of data which is relevant, then we can establish more complex networks. So how can we tackle such a problem? So instead of using a single network, we can use whole bunches of them. Then using Bayesian model comparison, we can compute the evidence for each of them, can compute which network is the most likely given the data, and we can also superimpose the different network responses weighted by how likely the network is. So if a network is producing deviating results, it's automatically discounted. So here is now example from speckle interferometry. Speckle interferometry is a technique where you can measure small distortions in a sample, also not only from nicely reflecting samples, but from rough ones. So that's very nice if you want to have a remote detection of surface modifications where you have to do that remote and where the surfaces are, let's say, dirty. And a typical problem in the evaluation of that data is how many interferometric patterns are there, how many fringes can be seen. The drawback of speckle is that the signal to noise ratio is very bad. So essentially it can be approaching 1. And so the typical question is, let's assume you have an image like here on the left-hand side, how many fringes are there? Or on the right-hand side, maybe you have a more complex pattern. Can you disentangle that? So that looks like a very nice task for a neural network, but you have only that single image. You don't have hundreds of images. You want to evaluate this one. So following the approach I've suggested before, you train a lot of different networks, different architecture, different number of neurons. You compute for all of them how well they do fit the one image, how likely these networks are. And this is what you see here on the right-hand side. You have in red, the red squares is the fit quality, the chi-square, and you see the more neurons you have, the better the fit is, as expected. The black bullets are how likely the different networks are, and then you see that beyond some region of, let's say here, 175 neurons, something like that, the model evidence is going down again. Here, the insert is showing close up. And then we can use all these networks and superimpose the output of these networks and see what is the response to the input. And that is what you see here on the right-hand side. Only input is the one image on the left-hand side, and this is now the output on the right-hand side of the superimposed networks, combined with a simple thresholding at 0.5, because the output has to be between 0 and 1 for this black and white image. And you see that without additional training data, something, you get an almost perfect result. We can compare that result with different approaches which are typically used for this kind of data analysis. The input was again this image which you see on the upper right. So where the flip probability was 0.54, so there's only a very tiny probability or very tiny deviation for 0.5, which would resemble random noise. And here you see different approaches using median filters of different bin width. And on the lower right, you see what the network response was. And we can compare that with the ground truth. And you see again that this is a very nice result. And essentially, there was no manual interaction at all. It was just this image, a bunch of networks being optimized, and there you are. So far, I was saying, okay, we were just computing the evidence for the different networks, but this is computationally extremely heavy because you have to integrate over all the possible parameters. And since we have here hundreds of parameters, this amounts to computing high-dimensional integral in that space, and this is very cumbersome. Standard Markov chain Monte Carlo won't perform well because the likelihood is sharply peaked, and the prior from which we sample is very broad. So the variance of the Monte Carlo, Markov chain Monte Carlo estimator is huge. So you need to apply either nested sampling or thermodynamic integration, which is very cumbersome. However, it turns out that if we just use the peak approximation, so evaluating the networks at the maximum likelihood value, then this results in a nice analytic solution, which is of course only an approximation. But for the task we had here at hand, it turned out to be orders of magnitude faster, and still yielding excellent results. And this is when the training, which can be of the networks, which can be done in parallel, is manageable, then computing this evidence in this approximation is definitely feasible. So this is why I think this approach is very nice. That brings me to essentially one of the final points of my presentation. Networks have the benefit that they always provide an answer. However, they have the drawback that they always provide an answer, even if the input space is far off the parameter volume where the training data were in. And this is raising the issue, how trustworthy is the result of a network. And if you want to apply that, for example, in a real-time application like we do for plasma tomography, then of course this is crucial if you want to control something with that. And here I would strongly advocate, given that one has in a Bayesian approach any way to train and compare a large number of networks, then using ensembles for that provide a very efficient online real-time check if you can trust the network. What you see here in the lower panels is essentially the discrepancy of the response of different networks in online reconstruction of a tomographic signal. And in the middle frame of the upper row, here you see the discrepancy between the networks for a given input sequence, and the reconstructed plasma emissivity is almost coinciding. If we now impose some signals which are, let's say, from a plasma regime which has not been trained on, then you see that the discrepancy is immediately growing. And this is something which you can monitor in real time and then decide, okay, at that stage, we don't believe the network output at all. There is something going on where the networks are not happy with. So because the output doesn't agree reasonably well, so we don't act on that information. And this can be nicely used as a kind of novelty or outlier detection, which can then subsequently be analyzed. And that brings me to my conclusion. So I hope I could show you that within a Bayesian probability framework, once you have prior, you can come up with a consistent and quantitative cycle of scientific inference. It has the benefit that you can include prior information of all kinds. It has the drawback that you have to include prior information. And so far, that was not really possible for neural networks. And I hope I could show you that if you have this invariance requirement, that you can derive a prior probability distribution, which performs quite well. And in that sense, I would say now Bayesian networks allow to bring the full power of Bayesian inference to the problem at hand. And it is perfectly suited to nowadays computing landscape, because most of the computational effort parallels very nicely. So there is not much overhead compared to training only a single network. And with that, I say thank you very much.
Great, thank you very much, Dr. Van Tuysen, for an exciting presentation. So let's proceed on to some question and answers. I think there are some questions being posted. Sardar, maybe do you want to just maybe unmute and ask the question directly?
Yes, can you hear me?
Yes.
Yep.
So you seem to have used the regularization term post hoc to choose a model out of many. Have you tried to incorporate the regularization during the training, like it's usually done with L1 and L2
No.
regularization term?
Sorry, no. It is applied during the training.
Okay, so is it both? Like, because it seems like also you also derived or trained like a lot of models, and then you chose one or a multiple.
No. There is no need to choose one. So maybe I should describe that in slightly more detail. So the additional prior is part of the model specification. And so each network is optimized with respect to the model fit, chi-square, and the prior probability of the weights. But what is but it's not a single model, but there is a whole bunch of different networks with different number of layers and different number of neurons being optimized in that way. And each of these networks at the end have evidence, so model probability, which is computed by both quantities, the goodness of fit and how likely these parameters are. And according to that, all the models are ranked and weighted.
Thank you.
Maybe I'll follow up on that question a little bit more. So, Dr. Van Tussen, are you then doing a Bayesian model averaging with the model you have? Kind of, okay, I see. And do you have any comments about how do you go about choosing this ensemble of models to begin with? Do you have any, like, does let's say the model space you're considering would make a big difference on the results?
Yeah, so essentially what you start with, let's say, it depends how many parallel computing power you have. So if you have, let's say, the capability of computing 10 different models, then you just start 10, 50, 100, 200, 300, each time 3 models or so. And then you see how consistent the evidence is, because it's an optimization after all, so you can get stuck into local optima. What you, for example, can see here, if you look at the chi-square, for example, there are chi-squares which are slightly higher with a larger number of neurons than with a smaller number of neurons, which of course immediately implies that this is not that this is a local optimum, but not a global one, because with more neurons, you can always improve the chi-square. So here you see already that you can get stuck in local optima, so that why one should always use multiple models. And then you see relatively easy the generic shape of this model evidence, or also of the chi-square, is always the same. Initially, if you have too few neurons, then you get a very bad fit. And then eventually the fit quality improves only very slowly with increasing number of neurons. So it flattens out. And then only at that stage, the penalty by the model complexity is winning, because if you look at the equations, the chi-square enters in the exponent. So, and the model complexity is only geometric. So it's a volume factor. So as long as you improve upon chi-square, model evidence doesn't do a lot. Only if the misfit is saturating, then the model evidence starts to dominate. And in that sense, you can relatively easy screen how complex your models have to be at least in the right ballpark.
Great, thank you. I think Alex, you have your hand raised. Go for it, Alex.
Thanks. So I had a question. You talked about creating a prior using the invariant structure.
Yep.
Maybe you mentioned this, but I missed it. How do you ensure that that prior is consistent for other things? So for instance, in a lot of these different structures with different sizes, a larger size contains a model with the smaller size. are you ensuring that the priors are consistent with the fact that they're essentially subsets of models here?
Let's say the prior is on the level of the initially on the level of the individual neurons. So each neuron is taking an input vector and is forming a decision boundary. What the neuron does, or this prior does, is it ensures that this individual neuron is acting under this prior in such a way that a priori all possible decision boundaries are equally likely. And then one combines these individual priors for the neurons. The, let's say, subset consistency is not imposed.
Thank you.
Oh, right. Oh, I see Jeremiah have your hand raised. Jeremiah, go for it.
Hi, thanks, Dr. Toussaint, for your presentation. I was curious, so in this slide, actually, when you were describing calculating the log evidence, you said that tools like MCMC were maybe insufficient for calculating this term. Like, what are the computational tools that you use for calculating the log evidence? If I have a given like Bayesian ANN, like how can I calculate its log evidence to weigh against other Bayesian ANNs?
Okay, the thing is why evidence calculation is hard, because in many standard MCMC approaches, the quantity you're averaging over is varying on a is varying slowly compared to the probability distribution and for which you sample. Evidence is, and so you need only a few samples and then you get already a pretty good estimator. Evidence calculations are the opposite. The likelihood is varying very rapidly and you sample from a slowly varying distribution. That means that you hardly ever get a relevant sample point, and that makes it tricky. What we have applied here is good old thermodynamic integration, essentially where you have intermediate smoothing distributions to approach that target distributions which you are interested in. Presumably nested sampling nowadays would be an attractive alternative options, but that's one I haven't used myself. And as I was pointing out, it, at least for the problems we have been using that approach, the much simpler semi-analytic maximum a posterior distribution and then computing the Hessian at that point turned out to be surprisingly good. There can be many reasons why it fails, but here it appears that maybe similar to the reason why networks are performing quite well, despite the fact that one presumably never reaches a global optimum, maybe for the same reasons, but that's just pure speculation. This second order approximation does the job, and so we have slightly abandoned the business of computing this 10,000 dimensional integrals. But of course,
yeah,
this is just, it's maybe not the best scientific answer. Of course, one should always aim for the exact solution if possible, but yes, you get lazy a little bit.
That makes sense. And it sounds like maybe with some of the like variational methods, maybe there might be a slightly easier way to calculate that evidence.
Could be. The problem I see here is if you look at that prior, which is also sketched at this graph here on the right hand side, it starts to drive weights and cells to zero if they are not required. So the tendency to cancel weights is becoming increasing, is a singularity. It's a 1 over x approaching 0 term here. And I have the suspicion that this may cause trouble in the standard variational approach. You also see that it does not really nicely disentangle into a product of individual factors. So my suspicion is, so the answer is twofold. A variational approach would be highly beneficial. To my knowledge, and at least in our group, it has not yet been attempted. And there may be reasons why it can be challenging, but I wouldn't exclude that it's feasible, maybe with a kind of switching. Once the weights are too small, just erase and a whole cell and proceed from there. But I think that is a very interesting research question, which hasn't been tackled yet.
Gotcha. All right. Thank you very much.
Great, thank you. Any other questions from the audience? Okay, so I think we are just over the hour. So I think we would end the seminar at this point. So thank you very much again, Dr. Wang Tusan, for a great presentation.
It was my pleasure.
Yeah, I wish you can come visit in the future in person as well. So with that, I think then we are going to wrap it up.